Okay, so this video is going to cover Chapter 5 of Geometry, specifically 5.4 through 5.7. By the end of this video, you'll know the 4 rules that can be used to prove congruence of 2 triangles, as well as how to do a flowchart proof. So, first we're going to start out with the SSS, or side-side-side congruence conjecture, which states that if the 3 sides of one triangle are congruent to the 3 sides of another triangle, then the 2 triangles are congruent. So essentially, if you know this, that you have 2 triangles and the sides are congruent, then you know this. Essentially, that this angle is also congruent to this one to this one, and this one to this one. So all parts of the triangle are congruent. They're congruent triangles. So another thing that's important that's going to come into play is the symbol of congruence, which is this. So for example, if this is triangle ABC and this is triangle DEF, then we can say that triangle ABC is congruent to triangle DEF. So now we have SAS, or side-angle-side congruence conjecture, which says that if 2 sides and the angle between them in one triangle are congruent to 2 sides and the angle between them in another triangle, then the 2 triangles are congruent. So say that we have these 2 triangles, and we have this side congruent to this side congruent to this side. We don't know about these sides, but we do know that these 2 angles are going to be congruent. Then we can actually say that these 2 triangles are going to be congruent based on this conjecture. So now you might be thinking, well, what about side-side angle? Well, okay, that might seem logical. If you have these 2 triangles, then, well, you have this side is congruent to this one here, and then you have an angle here. Well, what we could do is actually say, okay, well, how can we make a triangle that fits the same criteria but isn't congruent? So what if we took this side and moved it this way? It's the same length, but it forms this triangle, which definitely isn't congruent to the other ones, but has the same congruent angle, side, and side. So as you can see, side-side angle does not work as a congruence conjecture. Okay, now we're moving on to the ASA, or angle-side angle congruence conjecture, which states that if 2 angles and the side between them in one triangle are congruent to 2 angles and the side between them in another triangle, then the 2 triangles are congruent. So let's look here. If we have these 2 triangles, and we say that this angle is congruent to this one, this side is congruent to this side, and this angle is congruent to this angle, then there really isn't a way for these 2 sides and this angle not to also be congruent, and for the triangles to be congruent. So even here we have side angle angle, and that is a congruence conjecture that will work if 2 angles and a side that is not between them in one triangle are congruent to the corresponding angles and side in another triangle, then the 2 triangles are congruent. So notice it says the corresponding angles and side, so it's not just a random set of sides, side and 2 angles, it's the corresponding ones. So that sort of limits this, but that's how it works. So if we have this angle and this angle congruent to this angle and this angle, and then we have either this side congruent to this side or this side congruent to this side, then we can know that these are going to be congruent. So now really the only one left is angle, 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 and you might be thinking, well, if side, side, side works, then maybe angle, angle, angle does too. But let's look here. So if we have, say, a small equilateral triangle, so we know that all of these are going to be 60 degrees, it's very easy to draw a large equilateral triangle with exactly the same angle measures, but they're definitely not congruent because, well, this side is obviously not the same size as this one. Okay, so now we're going to do a practice problem. So say we have this triangle, and this is triangle SNL, and then we have a smaller triangle inside that looks like that, called TIE. And then we're asked the question, we're given the information that triangle SNL is equilateral, and we're asked the question, is triangle TIE also equilateral? And then we're also given the information that these sides are all congruent. So with this information, it's actually pretty easy from here. So we know that triangle SNL is equilateral, and if these sides are all congruent, that means then these have to also be congruent to add up to the equal measures of an equilateral triangle. We also know that these angles are all going to be the same because an equilateral triangle has all 60-degree angles. And then we can use what we just learned, which is side angle side here, to show that if these have a congruent side angle and side to these two triangles, then these sides are also going to be congruent because they're going to be congruent triangles. And then we can answer the question, which is triangle TIE also equilateral? And the answer is yes. Okay, so for the next thing we're going to cover is flowcharts. So a flowchart is a sort of concept map that shows a step-by-step procedure through a complicated system. Basically, it shows how something will cause the next step. And then a flowchart proof is a logical argument presented in the form of a flowchart. So next we're going to look at an example. So proofs are going to be really important in geometry. They're really the essence of applying what you've learned to make new conjectures. So here, if we have this shape here, and we're given that AR segment is congruent to ER, and EC is congruent to AC, and we're asked to show that angle E is congruent to angle A. So, okay, so we start out with our given. So here we have, so this is setting up for a flowchart proof. We have one, that AR is congruent to ER. So that's a given. And then we have 2, that EC is congruent to AC, and that's also a given. And then we have 3, that RC is congruent to itself, RC. So that's not given, but it's the same segment. And then these all lead to the next step, which is that, so for that triangle RCE is congruent to triangle RCA because of the SSS congruence conjecture. So we always write our reasons before or below each statement that we make. So here, if you're having trouble following this, so we have AR is congruent to RE or ER, and then we have EC is congruent here, and then obviously this one is congruent to itself. So then by SSS, we know that these are congruent triangles. And then that leads us to be able to say that, so 5 angle E is congruent to angle A, and that is by CPCTC. So CPCTC is something that you're going to hear often probably. It's really important. It stands for corresponding parts of congruent triangles are congruent. So seeing that we have these two triangles as congruent, these corresponding angles here and here are going to be congruent also. Okay, so now we have one last conjecture about isosceles triangles. So it's the vertex angle bisector conjecture, which says that in an isosceles triangle, the bisector of the vertex is also the altitude to the base and the median to the base. So if we have the bisector here of the vertex, so this is the vertex angle, and here we have a bisector, it's also going to be the altitude to the base, so it's going to have a right angle here, and it's going to be the median to the base, so these two parts are going to be congruent.